A girl stands on a platform in a classroom and she throws a ball vertically downwards to the floor, hoping that the ball, after it bounces, will hit the ceiling. Okay, so let me try explain. We've got a person, so there's a girl standing in a classroom, and she's standing on a platform. Okay, so she's standing on this platform over here, and she's going to throw this ball. She's going to throw this ball down, okay, and she's hoping that when the ball bounces back up, it can go up to the ceiling. Now, if any of you immediately say that it's not possible, let me just quickly correct you there. And I understand why you're saying that. It's because we've looked at questions in the past where if she takes this ball and she just lets it go, so she doesn't throw it, she just lets it go. There's a big difference there, right? Between whether you throw something down or whether you just let it go. If you just let it go, then it would never be able to bounce higher than it started. But if this person throws it down really hard, then of course it can bounce up higher than where it started. Okay, so just to clarify that over there. Then it says she throws the ball with a velocity of 8 meters per second. Okay, so we know that the initial velocity here is going to be 8 meters per second. From the height of 1.8 meters above the floor, yes, ignore the effects of friction. Okay, the first question says write down the magnitude. That just means you don't have to give a direction. And direction. Oh, okay, well then, okay, why don't just call it velocity then? Oh, it's acceleration. Okay, so right, the magnitude and direction of the acceleration of the ball immediately after the ball left her hand. Now, this shouldn't take you a long time at all. You're literally just going to say 9.8 meters per second down. Why? Because this is the chapter of vertical projectile motion. And after the ball has left the person's hand, whether the ball is moving up or down, we know that gravity is trying to pull it down. That's just a constant thing that we know about this chapter. We don't have to calculate acceleration. It's a given. 9.8 meters per second down. Next question. Is the motion of the ball while moving downwards towards the floor a free fall? Answer yes or no. Yes, it is. Because free fall, so we're going to say yes. Or you could say here, yes. Now, what is free fall? We know that free fall is when an object is moving under the influence of gravity only. Because once that ball has left her hand, after it's left her hand, what forces are acting on that ball? Don't say applied force. It is only an applied force when it's in the person's hand. After it is left the person's hand, there is no longer an applied force. Okay, so there's no applied force. You might say air resistance. Now, technically you are correct, but we ignore all forms of friction and air resistance for this chapter in grade 12. The only force acting on objects in this chapter when they have left the person's hand, for example, and if they're not touching the ground, because obviously when they're touching the ground, there's going to be a force of the ground. But when they're just moving through the air, the only force is gravity. And that is considered to be free fall. So free fall, or let's actually say, they said here, is it free fall? We can say yes, the object is moving under the influence. You could say a gravitational force here, or you could say gravity. I'm going to say under the influence of a gravitational force only. This next one says calculate the magnitude, so we don't need to give a direction, of the velocity with which the ball hits the ground. Okay, so they just want to know from there to there. What is the velocity when it hits the ground? Some learners often like to say 0, but that's not true. They're talking about that split second moment before it touches the ground, or as it touches the ground. Okay, that's what they mean. Okay, so of course we need our equations of motion. So we don't know the time. We don't know any time over here. So I'm not going to try to use this formula. I'm not going to try to use that one. I'm just going to go straight for this one over here. Why? Because it doesn't have time. So first step is I'm going to write my equation down. Okay, and then I'm going to choose a direction. I'm going to choose down as positive. You can choose up if you want. Now, we're trying to find the final velocity, which is down here. And the initial velocity is where we start. So that's 8 meters per second squared. Now, acceleration is going to be a positive value. Why? Because we're choosing down as positive, and we know gravitational acceleration always acts down. And then this distance here is also going to be a positive 1.8. Okay, so now we're going to go type all of this on the calculator, and then we're going to square root. Okay, so I'm just going to go straight into square root like that, and so this will give us 9.96 meters per second. Now you don't have to say down because they said only magnitude. The next one says, how long does it take for the ball to hit the floor? So what they mean there is, how long does it take to go from the top to the bottom? Okay, so I'm just going to go straight. I mean, there's a couple formulas you could use here, but I'm just going to go straight to this one. So my first step is I write down the formula. My next step is I'll choose a direction. I'm going to stick with down as positive. Okay, now I know the final velocity we calculated as 9.96. The initial velocity is 8, and gravity will be positive. And now delta t is what we are trying to find. So I'm going to take this to the left, so we end up with that over there. And then we have that. Now, this will give us that. And now you just divide both sides by 9.8. So you divide by 9.8, divide by 9.8, so that those would cancel. And so for your time, oh, it's a lovely answer, 0.2. And then that would be seconds. So 0.2 seconds. Now, moving on, it says that the ball bounces inelastically. That word there should not scare you. Almost all bounces, or in real life, and in a lot of these questions, most of them are inelastic. Let me quickly explain. If you have a floor and you take a ball and you throw it down towards the floor, or even if you just drop it, when it hits the ground, it's going to obviously bounce back up. But the velocity that it hits the ground is usually going to be much larger than the velocity that it bounces up. That's just due to energy that is being lost as the ball hits the ground. That is called inelastic. So here we know that this ball hits the ground at 9.96. So it is impossible for that ball to bounce up with a larger velocity than 9.96. In an ideal world, it could bounce up at 9.96, but in most situations, it's always going to be a little bit less. So maybe it'll bounce up at 7, maybe it'll bounce up at 6. We don't know. We're obviously going to have to try. Oh, it says here, the velocity decreases by 20%. Okay, so we'll just have to decrease this by 20%, and that'll help us to work out this velocity that it bounces up with. Pretty straightforward, okay? So that word there mustn't scare you. You don't have to think about, oh, now we have to go work out the energy and the joules. No, that's from momentum and impulse. Here they're just trying to describe the kind of bounce that we have. And most situations in these questions is always going to be an inelastic type of bounce. So this question here says, determine by means of calculations, whether the ball will reach the ceiling after its first bounce. Okay, so that's pretty straightforward. All we're going to do is we're just going to decrease this by 20% so we can work out what this velocity is when it bounces up. Okay, so there's different ways you can do this. You could say 20% of this number, and then you can minus it from this value. But what I'm going to do, if you take 20% away from a number, how much do you still have? 80%. So I'm just going to work out 80% of 9.96. Now I know that that just means 80 over 100, for example, and of means multiply. There's different ways you can do this, all right? So you should end up with 7. I'm going to keep all of these decimal places, 7.968 meters per second. So that is the velocity that the ball is going to leave. And as I said, you could have taken 20% of this number and then subtracted. That's all going to give you the same value at the end of the day. So that's the velocity that it leaves. So let's just quite quickly draw a picture for ourselves here. We know that it hits the ground at 9.96, and we know that it bounces up at, what did we say? 7.968. Okay. Now, determined by means of calculations whether the ball will reach the ceiling. Okay, so the ceiling is 3.5 meters away. So all we do now is we're going to go get our equations of motion, and we're going to find an equation that will help us to work out, for example, the displacement, and we can see whether we're going to get 3.5 or more. Maybe we even get more. That'll definitely tell us that it does reach the ceiling. Okay, there's different ways we could do this. Let's go get the equations of motion. So here we have them. So what we could do is, okay, we don't know time. We don't have time, and we don't have, or let's use this one. This could work. Check this out, guys. What we'll do, there's many ways you can think about this, but what I'm going to do is I'm going to pretend that the ball, because I know that when this ball leaves this ground, when it gets to the highest point that it can go, what would its velocity be? What is the velocity of a ball when it reaches its highest position? 0, right? But I don't know where that's going to be. It might be here. It might be here. I don't know how high that ball could actually go. Forget about the fact that there's a ceiling. Let's just see how high that ball could actually go. So I'm going to use this formula here, and I know that wherever its highest point is, it'll have a velocity of 0, right? Okay, so 7.968, let's just remember that. 7.968 is the velocity down here. 7.968. Okay, so forget about the ceiling. Let's go see how high this ball can go. So we're going to go Vf squared equals to V initial squared plus 2a delta x. Now, here's where things get interesting. A lot of learners, they think that because we chose down as positive for the previous questions, now they think that they have to choose down as positive again. We can if you want. There's no problem with that. I just usually like to, if possible, I like to choose, the direction that the ball is moving. It just makes life a little easier, and there's less things to think about. But if you want to, we can choose down as positive again. I wouldn't do this if I was by myself. Like if I was just doing this question, I would actually have chosen upwards as positive. But I know a lot of learners like to stick with one direction. I've seen that a few times. Okay, so let's try that and see how it goes. It's going to be a bit weird, but then I'll do it for you where we choose up as positive as well. I'll do both, and then you'll see. Okay, so the final velocity I know is going to be 0. The initial velocity is 7.968, but it's going to be negative. Why? Because that velocity is going up, but now we've gone and chosen down as positive. You see how it's already getting a bit weird, but it does work. Acceleration is going to be 9.8, and it's positive because down is positive and acceleration is always acting down. Now, here's where learners are going to make mistakes. A lot of the time, I've seen this a lot. We're choosing down as positive, but the ball is going to go above its starting position. So the displacement is actually going to be that's what we're needing to calculate. Never mind. We're busy calculating that part. Okay, so now if I take this over, well, let's first go calculate all of this. Okay, so that's going to give us 0 is equal to 63.489024. It's a positive. Make sure you put this in brackets. And then this will become 19.6 delta x. And take the 63 over to the other side. Okay, now just divide both sides by 19.6, and what we should find is that delta x will be, so you'd end up with a negative 3.24 meters. Now remember that we chose down as positive. You're getting a negative answer, so that just means up. Technically, it means above. When you're talking about displacement, it means above your reference position, which we were choosing as this one here. So, but we can just say up for now. So delta x is going to be 3.24 meters up. So can you see that 3.24 is the highest that ball would reach before it reaches 0 velocity? So 3.24 is less than 3.5. So will the ball reach the ceiling? No, it won't. So you would do that whole calculation. You would then say, therefore, this is smaller than 3.5, therefore ball will not reach ceiling. Now, if you wanted to choose upwards as positive, which is what I would have done, just because it feels more comfortable, let me just show you how that would have played out for you. there would just be less negatives. Okay? Because check this out. If we chose upwards as positive, then your VF squared is still 0. Your initial squared is now going to be, what was that value? Oh, there, 7.968. But now it's positive because we chose up as positive and it is moving up. See? Now, acceleration, that's the one you got to look out for. If we choose upwards as positive, we know acceleration always acts downwards, and then you would have delta x. Okay, to be fair, it's not that much better. So then you would just go solve, blah, 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 blah. But when you get your answer now, you would actually get a positive answer, which means if we chose upwards as positive, then that means up. So you get the same answer. So yes. End of the day, you must do whatever's comfortable for you. So we're just gonna summarize here. Obviously, for 5 marks, you would have had to show everything, but we're just gonna say no. And then I just want to remind ourselves, what height did we get? We got 3.24 meters. Now, obviously, that's not going to get you 5 marks. The 5 marks is from all of the steps that we showed. Okay. So let's move on now. Now, this one says, sketch a velocity time graph for the motion of the ball from the time the ball is thrown until it reaches the maximum height after the bounce. Clearly show the following on the graph. Okay, and then we'll make sure we show all of these things. All right, Kevin, you sound like you come from Joburg, bro. Yeah, see. Gonna go play some ruggers this weekend with the boys. Well, actually first, bro, we're gonna pop in at the gym, pop in some bench press, bro. I'll bench you for a warm-up, and then we can play a bit of ruggers. And then afterwards we can head out to one of the pubs, bro, and just grab a few dops, and then, yeah, bro, lekkers, huh? Okay, this is really cringy. I'll show you this velocity time graph based upon if you choose up as positive or down as positive. So if we choose down as positive, then the initial drawing of the graph looks the same. We have a y-axis and an x-axis. So time and then velocity. And that's in meters per second. Okay, so it's really easy. Check here. Sketch a velocity time graph from the time the ball is thrown. So immediately when it was thrown, what was its velocity? 8. Now be careful. Was it 8 down or 8 up when the person threw it for the first time? It was 8 down, and we just chose down as positive. So that means we're going to put a little 8 over here. You're not going to put it down here at -8. No, that's only if we chose up as positive. We chose, okay, let me slow down. I feel like I'm throwing in too many terms. Okay, we chose down as positive, and the ball is moving down here, so it's a positive value. We don't put it as a negative. No, we chose down as positive, and the ball is moving down, so that's why it's a positive value there. Now, think about this. Because a lot of you are immediately just going to start drawing a line that way, because that's what you've seen. But be careful. What is this ball going to do now? Is it going to become faster or slower as it begins to fall? Well done if you realize it's going to go faster. So you wouldn't go this way, because then your velocities are going 7, 6, 5, 4. No, we want to go faster. We want to go 9, 10, 11. So we're actually going to go that way. So it's going to go like that. Okay? Now, when it reaches this point over here, we know that its velocity was 9.96. So we can put that as 9.96. Okay. Now, if we choose down as positive, I will show up as positive next. Okay. So we now reach the ground. Immediately, now here's where learners get confused, but it's also one of the easiest parts, so just listen up carefully. It's an easy thing to fix up if you're struggling to understand this. This 7.968, is that going to be up or down? Remember, it hits the ground at 9.96, so that was down, but then it bounces up at 7.968. So this is going to be when it's going up, but we chose down as positive. So normally you would just go dot, 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 and you would go vertically downwards to somewhere over here. But when they give you a collision time, sometimes the time is not immediate. They gave us a little bit of a time. Then your graph is going to go a little bit slanted at that point. There we go. And then you're going to go to about there, which is going to be negative 7.968. Because at this point, the ball is going to go up, but we said down is positive. That means up is negative. So anytime you're moving up, it's negative. And normally this line is vertically down to there. But because there's a collision time of 0.01 seconds, the time axis, it has to go a little bit to the right. We'll fill those values in now. Okay. Then, what do they want here? Clearly show the following in the graph. The initial, the velocity and time when the ball hits the floor, the velocity and time when the ball leaves the floor. Oh, okay, well, that's all that we need. We don't need to do the part where it goes up again. Okay, so let's go fill everything in. So what is the initial velocity of the ball? 8. We've got that. Fantastic. The velocity and time when the ball hits the floor. So we've got the velocity when it hits the floor, but we don't have the time. So let's quickly go get the time, which would be this value over here, which was, oh yes, calculate how long it takes to hit the floor, 0.2. So we can put 0.2 over there. Then, what is the velocity and time when the ball leaves the floor? Okay, well, it's going to be 0.2 seconds plus 0.01. So that'll give us 0.21 for the time over there. And the velocity when it leaves the floor is that part over there. So this is on the floor, and that's also on the floor, okay? And then that's all that they want. And then they also say here, I nearly missed this, until it reaches the maximum height after the bounce. Okay, so now that the ball is over here, it's going to start going up. And what happens to its velocity as it goes up? It becomes less. So how will I show that? I'm literally just going to start going like that. Let me explain. If I read off these velocity values, they would be like -6, -5, -4, -3, for example. The negative just means we're going in the opposite direction to what we chose as positive. And then when it eventually reaches its maximum height, which we found out earlier was like somewhere over here, what was its velocity there? 0. And can you see here? Our velocity here is 0. And so that's all that they want on the graph. So the graph's going to look like that. And then they wanted these 3 important points, and so that's it. So now I'm going to quickly show, for those of you that want to know what the graph would look like if we chose upwards as positive. For those of you that are happy with what we've done so far, then the question is technically finished. Now, for those of you that would prefer to choose upwards as positive, then everything up is positive and everything down is negative. So when we look at this beginning stage where the ball gets dropped at 8, remember that's 8 down, and down is negative. Now, in this type of situation, so we'll actually start our graph here. Now, be careful. Don't just think, oh, I'm going to go that way. What is the ball going to do now? Is it going to become faster or slower? It's going to be faster as it begins to fall. So the velocity is actually going to go like this, because think about it. -9, negative whatever, like -10, -11. The negative just means the direction. So the graph won't go this way, because if it went that way, then you're going 7, 6, 5, which is slowing down. So it reaches the ground at 9.96. So let's just put here -9.96. So this is where it reaches the ground, okay? And we know that it took 0.2 seconds to reach the ground. So we could put 0.2 seconds over here. Okay, now immediately when it hits the ground, it's going to do what? It's going to bounce up. At what velocity did it bounce up? Well, we calculated it like that. But because it's going to be going up, that's now going to be a positive value. So our graph is immediately going to go, now listen carefully. Normally you would go dot, 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 and you would go straight up. But in this type of question, and they do this a lot, they tell you here that the collision is going to last for 0.01 seconds. That means that the collision part, it's not going to be immediate where you just have a dotted line going straight up. Instead, your dotted line is going to be a little bit, it's going to go a little bit slanted. So it's going to be more like that. Okay, and then it's going to go up to 7.968. 7.968. And for those of you that wanted to choose downwards as positive, remember I did show that in the previous, I showed that just before this graph. in case some of you fast forwarded to here and you're like, Kevin, I want to choose down as positive. Okay, so now we're going to be there, and we know that this point here, this value is going to be 0. Well, we know that this one was 0.2, you know, when it hit the ground over there. And then when it bounces up and it's this one, that's going to be 0.21. So over here we could say 0.21. How did I get that? I just said 0.2 plus that. Okay, so now the ball is over here and it's on its way up. So as it's on its way up, what is happening to its velocity? Well, now it's going to start slowing down. So it's going to go 7.968, then it's going to go 7, 6, 5. So it's going to start slowing down, and eventually it reaches its highest point over here where we said the velocity will be 0. So we're just going to go to there. Now let's make sure we have everything important that they want on the graph. The initial velocity of the ball, yes, we have it there. The velocity and time when the ball hits the floor for the first time, yes, that was the 9.96 and the 0.2. We've got that. The velocity and time when the ball leaves the floor, that was the 7.968 and the 0.21, so we've got all of that.